Yo, what's going on, guys? Welcome back. Today we are on day 14 of the Cyber Advent Calendar. So keep in mind, I'm trying to knock these all out, so you may get a bunch of them. I may not finish them all, just depends on how much time I have. Obviously, holidays are busy. So let's hop into it. Let's talk about this one. This one is machine learning. So hit that like button, hit that sub button, guys. We are almost to 11K subs, and I am going to keep uploading regular content. Keep in mind, it's just a busy holiday season, so when the holidays come around, it's a busy time for cyber, it's a busy time for me, it's a busy time for you. So I try to get as much of this stuff done as I can because I know a lot of you want to enter this to get the prizes. So all right, so first one, this one is on machine learning. So this is on AI, as they call it, right? There's a couple of things. One thing I'm very glad they did in this box is they specifically laid out that AI is used incorrectly all the time, because I don't know why. I have no idea why, but it's a pet peeve of mine. It drives me nuts that people say, hey, dude, have you seen AI? Have you seen AI? AI is not what you're talking about. You're talking about machine learning. There's a big difference. Artificial intelligence means it's intelligence that's artificial. There is no intelligence in machine learning. GPT isn't intelligent, right? It's just reiterating answers that it learned for you. So let's go ahead and talk about it, and then we're going to go through and we're creating our own AI. I think the lab itself is pretty poor, but I think the explanations are good if you're trying to get into AI. So first things first, they say right here, there's often shrouded in mystery. AI is often shrouded in mystery, machine learning, leading to a lot of snake oil tactics. If you don't know what that is, it means they're selling you bull crap. That's what it means. In this task, we'll provide a glimpse into the world of machine learning to help demystify the incredible topic. So this is true. Here it is. The term AI is used in broad strokes, meaning it's not used correctly, often incorrectly. We have to be honest with ourselves. AI cannot just be a bunch of if statements. You can't just say, if someone asks you this, answer this. That's not AI, right? It can give the presentation of AI. So a good example of, if you've never heard, is I've always heard the Chinese room experiment, whatever. It's not a real experiment, I don't think, but it's a theoretical experiment. So let me ask you this. If there's a door in front of you, and it's just got like a mail slot like some doors have, right? And you're write an entire paragraph or sentence in Chinese lettering, right? And slide it through the door. And the person on the other side of the door does not speak a lick of Chinese, doesn't know anything about it. And they have a Chinese dictionary, and they go through and can decrypt everything you said, right? And they write it in English and slide it back through that door, right? Does that mean on your side, think about it, what would you think? You'd think that person knows Chinese because they just translated it for you, right? They just gave you the answer in English. But you don't know what's going on back there. So you don't know if that person knows Chinese. That's the same, and I know Mandarin and all that. It's an example, okay? So don't get crazy. But my point is, there's the perception that it knows more than it does. And we're going to cover some of that. So there's more than this, but this is the ones they're going to show. Genetic algorithms. So this is the algorithm where they aim to mimic the process of natural selection evolution by using rounds of offspring mutations based on the criteria provided. This structure creates the strongest child. What does that mean? It means it's going to give you the best. Like, it's only going to give you the best. So for instance, if you ask it a question and there's like 10 answers that it could be, it's not going to be like, well, you could be looking for this, 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 or this. It's going to say this is the answer. This is it, because this is the strongest one, right? Then there's particle swarm. Aims to mimic the process of how birds flock together at specific points, creating swarm particles. The structure aims to move all the particles to the optimal answer. So this is basically, hey, this is what everybody says, so must be accurate. Now, here's where the problem comes with the particle swarms. This is, and I don't know what algorithms and things like that ChatGPT and all of them are using, right? I would assume it's neural networks, but I don't know that. So the problem is, AI's been around for a long time. Or AI hasn't, but machine learning has, right? It's been around for a long time. Well, the reality is, what happens typically is this particle swarm attack, or feature, whatever you want to call it, effect. It gives an answer that everybody thinks is the best answer. Why is that a problem? Think about it, right? You're probably thinking, well, that makes sense. Like, if everyone agrees that's the best answer, it probably is. On paper, that makes sense. Think about the internet. If I go on the internet right now and I show a picture of a blue truck and I post it on Reddit and I say, what color is this? How many comments do you think I'm going to get that say blue? And how many of them do you think I'm going to get that are trolls? Right? That say, red, you're an idiot. Purple, you're an idiot. Green, you're an idiot. Whatever, right? Those answers get processed by this machine learning and it says it's red, right? And it says that because that is the most popular answer. So keep that in mind because it's scouring the internet. So that's what the particle swarm is. Now the neural networks, this machine learning structure is by far the most popular. Yep. Aims to mimic how the brain works, right? So there's neurons and they network to each other. You'll see. Okay, so then you have learning styles. So you have to teach the machine learning. It can't just all of a sudden know everything, right? You'd be sitting there programming for years if you needed to program every single thing it knows. So what you're going to do is you're going to do either supervised learning or unsupervised. Unsupervised, you just let it run and you let it learn as much as it can, right? It's going to start grabbing pictures and saying this looks like this and this looks like this and this looks like this, and it's going to be grabbing colors and say, well, this color is this color. It's going to be grabbing everything it can and trying to learn it, right? Then there's supervised learning. This is what you're going to see in a lot of tooling and a lot of like actual cybersecurity tools, heuristic behavioral analysis, that type of thing. You're going to supervise it. You're going to say, if you see this behavior, this is what it probably is. If you're going to see this behavior, this is what it is. If you see, for instance, instead of saying blue truck, ask everybody what it is, I'm going to tell you, I'm going to show you 5,000 pictures of this blue truck, different pictures, and I'm going to say this is blue, this is blue, this is blue, this is blue. And it's going to say, okay, I know what blue looks like because you showed me enough examples. All right. So now we have basic structure. So this is the basic neuron network that we're talking about. Now the story goes that they attack the Elf Lab, whatever, it's the toy shop. I don't remember how they worded it. And they're making defective toys. So we're using this machine learning to actually detect if it's defective. So we're measuring height, width, length, color scheme, the maker elf ID, and then the checker elf ID. And you see how they're all connected? Every one of these is getting some input. So we're going to input these, right? And it's going to every one of these nodes. And then something is happening. That's why it says hidden. And then we get the output. The output is it defective or not? So those are the layers right there. Now here's the hidden layer that you're not seeing, okay? You're not seeing where they're actually weighting the answers. And what I mean by weighting is like they're weighted. So for instance, you're in a toy shop. You make an elf, okay? He's 6 inches tall, okay? Well, the next elf might be 6 inches tall, but like 6 inches and 2 centimeters, right? So there's going to be a deviation. But the color, is the color red or is it blue? That's not going to deviate as much, right? Because they're using the same paint. The other thing, the maker elf ID, right? The maker elf ID might be weighted higher, might be worth more because the maker elf ID isn't going to change. There's not a chance that it's Scott making the toy, and then the next time Scott makes a toy, it's Scott with 3 T's. There's no chance of that, right? It's going to be Scott, 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 Scott. Tim, 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 right? It's going to be an elf ID every single time. So if you input the elf ID, that's going to be worth more than the height. Because, for instance, what if every time Scott makes one, right? He makes one, it's blue. The height is always just a little high because he makes it a certain way or whatever. Those things all get weighted in, right? So you can see that's what's happening at this hidden layer. They're weighting them. So you can see they're taking the input. So the input is weight is or the height is the first one's height, right? Yeah, 0.93 inches, and they're taking the weight, they're timesing it, and then there you go. And then now you're going to get an output that says how accurate you are to the real thing. How close are you to that real thing that we need? Because what we're going to talk about next is, well, we're going to talk about it here coming up. All right. So there's, as mentioned before, we'll simplify the math quite a bit. Yeah. Inputs are not directly added. Instead, they are multiplied by a weight first, meaning they are not taking, if you put 1 inch They're not taking it and inputting it as 1 inch. They're taking 1 inch, they're multiplying it by their weighted value, and then putting that in. The additional output is not directly transmitted out. Instead, the output first enter what's called an activation phase. They decide will be active or not. It does not ensure the output, blah, blah, blah. Yeah. Okay. So feed forward loop. The feed forward loop is how we send data through the network and get an answer on the other side. Okay. Once our network has been trained, it's the only step we perform. So we perform this, the input, right? At this point, we stop training and only want answers from the network. To complete one round of feed forward step, we have to perform the following. So we do the normalization. Okay, here we go. Normalize all the inputs. To allow our network to decide which inputs are most important in helping it decide, we need to normalize them. That's what I'm talking about. Determine what is the right value, right? So what we do is we put a standard. So we say, hey, when you make a ELF, it should be 0.4 inches tall, 0.9 inches long, and 0.02 inches wide. That's what they're doing here. And you do that, right? And so let's say you make 10 elves and you make them, those are your standards. And then they look at them and they say, well, they're deviating just slightly on this, just slightly on this, just slightly on this, but they're not deviating here, they're not deviating here, and they're not deviating here. Well, these are going to be more weighted then. They're going to be worth more, right? It's kind of like if you've ever heard of scoring on a curve. You're saying, okay, well, here's the deviations. Here's the deviations. Let's score based on these deviations, right? It's a little bit different than that, but that's a simplified way of doing it. Now, back propagation. When we're training our network, the feed forward loop is only half the process. Once we receive the answers from the network, we need to tell it how close it was. So we put these in. The network says, okay, here's what we say, and we'll tell it that's accurate or it's not. If it's not accurate, you're off by this much, whatever, it will correct itself. It'll say, oh, I'm weighting the length too much. I'm weighting this too much, right? So it will correct itself. So that's what the back propagation is. We're feeding it back in saying, you're wrong on this. You're wrong on this. That's the learning process. Okay. The data set splits. So the last topic we covered before we build the network is our data. Let's use an analogy. Let's say your teacher tells you, so this is 1 + 1 = 2, right? 2 + 2 = 4. But let's say you get told this 500 times, right? And then every time the teacher asks you, you say, yep, 1 + 1 is 2, 2 + 2 is 4, right? Let's say then they go, well, what's 3 + 3? Well, what they're saying is, did you learn how to add? Or did you just learn that 2 + 2 = 4 because she repeated it 500 times to you? That's what the risk that happens with neural networks a lot is too, is you feed it so much that it's not learning what color it is or what height it is. It's just repeating back what you keep telling it, right? It's not even trying to learn it anymore. It's just repeating it back. So you need to balance that, right? So here you have training data, you have validation data, and then you have testing data. And they're saying they need to split those, the data sets. They're splitting them up into different data sets. So that way it's not just getting all of this data and going, got it, I memorized it. It's actually learning based on different data sets. So putting it all together, here is the the script. That's what we're looking at here. We're looking at this script. Sorry guys, my my nose is stuffy. Get it? Okay, so now these are just imports. We're importing them. Here we go. We're importing libraries. That's fine. We don't need to really worry about that. These are the colors that we're going to use. Now, we will convert these later. We're going to cover that. They're going to convert them into integers. This is telling it to read the training data. Okay. This is telling it to read the testing data. This is just setting up the variables pretty much. And then here you're encoding. Now, why are you encoding? It's because the neural network cannot take strings. It's only going to read integers. So you need to encode them to make the colors integers. Okay, that's fine. Read our training data. So now we're going to actually read it, and they're going to get the height, width, length, color scheme, maker, elf ID, checker, elf ID. The same thing we covered before. Now they're going to go ahead and read the labels of our training data and try and figure out if it's defective. Now you can see here, they're going to read the testing data now. Same thing. They're just going to grab it, but they're grabbing it from a different data set. So what we need to do now is create the data sets. So we go down here and we go to where it says insert dataset split code. So we need to split up the data sets. Why do we do this? So it doesn't accidentally learn based just on what we give it and just memorize it. We need it to actually learn. So we're breaking up the data sets. We're going to say, hey, we have a couple data sets we want you to look at. So we insert the data set. So we'll go ahead and say, boom, insert that. And what that's going to do is just split them up. Easy. Now, normalize the data. So we need to actually normalize it so that it can understand. And if you remember, we can, each one of these steps, you can go back up. If you get confused, you're not sure, and look for the normalization step, which is right here. Nope, where was it? Here we go, normalization. So all we're doing here, we stop training, simply want an answer from the network to complete round one, blah, 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 we have to perform the following. So you do the normalization first, then get the input, then the hidden. What that's doing is it's, again, telling it what to actually do. So to allow our network to decide which inputs are most important. So again, if you don't say, hey, the color is the most important thing, then it's just going to say, okay, well, the height was off by 0.1 inch, so it's defective. It's a fake toy. Well, it's not a fake toy. There's just variations in that, right? Like, you can't make the toy the exact height every single time because that's not how a factory works. So you have to have variations, and you have to wait. And when I say wait, I mean like weighted, if you've ever heard that term. Not like wait as in hold on. I mean like weighted the actual results. So we have to take this, copy it. And it's kind of a pain that you have to copy back and forth this way. But this is why I say the lab, in my opinion, is kind of because all you're doing is copying, changing the code. You're not actually doing a whole lot, but it's interesting because they say they're at the end. I haven't done this yet, but they said at the end that you're going to see how close your accurate code was. So that's cool. So now we're going to train the neural network. So here we're going to say, finally, we train our network. First, we create our classifier with the following code. Okay, so we have to create the classifier first. All this is the classifier that's the solver, the algorithm to update the weights, the alpha. The alpha is used to for the regularization of the neural network. So to do exactly what we just said. Hidden layer sizes. This tells us the structure of the hidden layers. So this is, they have 2 hidden layers with 15 nodes each. So those nodes that you saw go down, those are the hidden layers. And then the max iteration, this sets a cap. So we don't want it to just keep iterating through the process over and over and over and over and over, because if you remember, it'll just start to memorize after a certain amount of time. Okay, so now we say, this is the classifier code. We got to copy it first. So this may seem very complex, and it can be, but all you're telling it is, hey, we're going to give you some data, review it, do this algorithm on it, and then when you have the algorithm, we're going to weight each piece, and then at the end, you're going to tell me how close it is to the original. And when I say original, that's just the standard we set. You can make the original whatever you want. Okay, that's classifier code. Oh, crap, I put that in the wrong place. So this, cut, there we go. Okay, now we need the classifier training code. Okay. And you're just copying, pasting. It's kind of a pain, but there's worse things to do. Okay, now the classifier validation prediction code. So this is to validate that it worked, that it can predict. Okay, insert. And they put, the nice thing is they did put comments in here for each one, like, hey, here's where you're going to predict it. So if you're struggling with this, just follow along. Now insert classifier testing prediction code here. Okay, where's the testing one? Insert classifier testing prediction code. So you can see they have a test and a validation step. That's why there's so many copy and paste, because they have the test and the validation. Now, if you just created this with just one data set and no test, no validation, nothing, what would happen is you'd have no idea if your answers are actually accurate or not. So that's why they have that validation step. They want to make sure. So now we've got it, and we can go ahead and we should be able to run it. Keyword should. Okay. Why can I not find, was it not on the desktop? Oh, it's in neural desktop, neural network. Okay, Python 3, detector.py, and we run it, and it's gonna go through all these data sets. Keep in mind, the data sets that it's looking at are these testing CSV, training data CSV. They're already in here for you. Don't move them. Don't mess with them. And you can see it's taking samples of our data. Boom. And all it's doing is taking everything we gave it and turning it into an integer form that it can then calculate. So it's just a calculation. It's just math. I say it's just math. I'm terrible at math. I mean, absolutely terrible. So I'm not saying it's just math in the sense of like, oh, anybody should be able to do this. This is math that a computer can do based on algorithms. It's not something that a normal person is going to look at and go, oh yeah, I see they're doing this, 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 and this. So if you look at it and go, I have no idea what's happening, mathematically, don't worry about it. Theoretically, you should worry about it. So now when you're done, it says these predictions will be saved to a file. Upload your predictions here. So we got to go to this website. While it's loading, we'll go to it. And if you're accurate up to 90%, you can see we're up 91%, we will get a flag. So looks like we were accurate enough. Oh, it already went to the website for us. So we'll go ahead and browse. And it looks like we were on predictions.txt, I believe. That wasn't in there before. We upload it and boom, there's your flag. So there you go, you get the flag. So all you gotta do is copy and paste the code. It works just fine. You just have to make sure that you're within 90% accurate. If you run it and it's not 90% accurate for some reason, try and rerun it. If your code is accurate, it will work. If your code isn't accurate, it won't. So just try and rerun it. But hopefully this helps you guys, and hopefully we can keep knocking these out. So have a great day. Thanks.